Hi, so welcome to section 5.2, medians and altitudes of triangles. Again, we're working in chapter 5, which is applications of congruent triangles to prove more relationships, or maybe not congruent triangles, but other relationships within triangles. So again, the first big theory, or first big standard here is proving theorems about triangles. We have two specifically in this chapter. And then using geometric methods to solve problems using constructions and everything like that. We'll do the more construction stuff on a couple days from now, but we'll come back to this. So you've used identify and use perpendicular and angle bisectors in triangles. Now we're going to use something called a median and the altitude of a triangle. And the altitude you already actually kind of know about, you just haven't called it an altitude before. So first definition, median. A median is a segment that connects a vertex to the midpoint of the opposite side of a triangle. So for instance, here's vertex C. Here's the midpoint of the side that's opposite of it, D. If I connect those two, I get what's called a median. Okay, and it should make sense. Median means middle. So we're talking about going from a vertex to a middle. Now I'm not perpendicular to the side necessarily. I don't necessarily bisect the angle as well, or either, but it goes to the middle. Okay. Now the other segment you should be familiar with is the altitude, because an altitude is just a fancy way of saying the height of a triangle. Now, we have a much more complicated definition for that. And it's because the altitude could be inside or outside of the triangle. Now, before I kind of go through what all this is saying up here in this definition, let me just look down at the drawing down here. This guy here is inside the triangle, the altitude is. Excuse me. When that happens, you just go from a vertex to the other side and you're perpendicular. So from the vertex to its opposite side, perpendicular to it. The problem is this: if you would be outside of it, if I go from B and try to go straight down perpendicular, I miss AC. Well, that's where you have this more expansive definition. So it says an altitude of a triangle is a segment from a vertex, okay, B, to the line containing the opposite side and perpendicular to that line. So actually what we really do for altitude is we really create a line for it, but how we do that is we think of the side as being extended forever, like that. Or in this case here, here's the side. I just keep going forever and ever. Okay, now BD is perpendicular to the line that contains that side. So that's how we get around it. And it could be in the interior or exterior, or if we actually have a right triangle, the altitude is here, it's actually a side of it. Okay. So the first thing we really need to be able to do is, looking at a drawing, given some information, identify the median, the altitude, the perpendicular bisector, and the angle bisector. Okay, so here's our first example. Right. So the first thing is they tell us a bunch of stuff up here. It says, use the diagram shown and given information to match the type of special segment with the correct segment. So we have angle BAE is congruent to angle EAC. So here is BAE. So this is kind of hard to tell, but here's BAE right there. I'll do a double one for it. Okay. And then it is congruent to angle EAC. So here's E to A to C, also congruent there. Okay. Now, what that's telling us is we have a pair of congruent angles. That means something's bisected, and hopefully you can tell the segment that must be doing it's EA or AE, however you want to say it, because that's what's in both of them. Which if I just draw down between them, right there, AE. So that's the angle bisector, which actually is B, it's AE, so angle bisector B. Okay. Now, the other piece of information they tell us, okay, excuse me, is that BF is congruent to FC. Well, here's BF, here's FC. Those two are congruent, which what that means is that point F, is a midpoint. So it's got two congruent segments there that meet at F. F must be the midpoint. Now that's important for two reasons. Two of our definitions, median and perpendicular bisector, depend upon a midpoint. Now the difference is this: the median goes from a vertex to that point. Well, what goes from the vertex A to that point? Oh, that's F, AF. Oh, there we go. There's our median, AF. The perpendicular bisector does not have to go through a vertex. That's the key with it. It just has to go through the side and then be perpendicular to it. Well, guess what? They give us a perpendicular line there. So GF is our perpendicular bisector. So D there. And then, last but not least, the altitude is the one that's left over. Obviously, it must be A. But if I look at the drawing, okay, from A to D, I go from a vertex, and I'm just perpendicular. I didn't cut anything in half. I didn't cut anything in half, basically is what it is. Either wasn't the median or the perpendicular bisector. I didn't cut an angle in half, that's for sure, because I only did the perpendicular business, so A is the altitude. So C, A, D, then B. Okay. All right, now, centroid theorem. Okay, I got another slide here in a moment that's got a little example of the centroid. Excuse me. But the medians of a triangle intersect at a point called the centroid that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so you'll see it in the drawing a bit, but yeah, you got 2/3 distance. So AK is a midpoint. Well, AP is 2/3 that length. CJ is a median. CP is 2/3 the length of that median, and BL is a median. BP is 2/3 the length of BL. Okay, so yeah, the median is also known as the center of mass. For a triangle, and the reason that's important is that's where you could balance a triangle at. Oops, I can't type. There we go. So it's also where you could balance a triangle at. Okay, so here's a little bit of a sketch for you here. So point G, I'm just going to rename that real quick. Object properties. Well, I can't really rename it because I've got. We'll just do this. G is the centroid. Okay, that works. So point G is the centroid. So here's the deal. From A to G, it's 3.47. From A to F, it's 5.21, and that is 2/3 the distance. So 2 to 3 ratio. And as I move it around, I change the length of these guys. Again, BD is one of the medians. Okay, B to D it's 5.65 whatever units this is. 2/3 of that is 3.76, and the reason I know it's 2/3 is because it's the ratio of 2 to 3. Same thing happens for CG. Okay, it is 4.54 right now, but that's 2/3 of CE, which is the whole length, 6.82. And no matter what happens, I change these measures here, but they always reduce to 2/3. Now there's some round off error going on in the background that we can't tell. The computer's cutting off numbers, but the computer is also not when it does the fractions stuff for me here. So here we go. Let's look at some examples. Okay. So in triangle ABC above, FC is 15. Find each length. Okay. Now this is the hardest part of the section, is using these theorems. So hopefully we can get this and it makes good sense. So here's what I know. Oh, they didn't tell us this, but Q is the centroid. I cut that out. Shoot. Which means this stuff here is congruent. This has been bisected. This has been bisected. So AD is a median, BE is a median, CF is a median. They all meet at point Q. So let's see what they tell us. They say that FC, all right, well, that's the whole length. So the whole is equal to 15. Okay. They want us to find two things, FQ and QC. Now, here's what the theorem says. It says the distance from the vertex to the centroid is 2/3 the whole length. So I know this, CQ, or QC is what I have in this problem, isn't it? QC is 2/3 the length of FC. Okay. So I actually can find QC first and help me find FQ. Well, QC is 2/3 the whole length. Well, if the whole length is 15, 2/3 of 15 is then going to end up being 10. So it's 10. There are no units to it, so it must be 10. Now, the other thing is this, if this is 10, that makes finding FQ really easy, because if this is 10 and the whole thing is 15, that means FQ has to be 5. That's it. All right, next one, same style of problem, just different numbers this time. So we know in the beginning here, before we even start, that P has to be the centroid, because all the sides have been bisected. They all have midpoints at S, T, and R, and you're going from the vertex to that midpoint, but none of the angles are shown as being bisected, so it must mean we're working with the medians here. Okay, so let's take a look. There we go. Sorry. So in triangle JKL above, RP is 3.5, JP is 9. So find each measure. Okay, so RP is 3.5. Okay, and then JP is 9. Okay, so he wants to find PL first. Now here's the deal. I didn't mention this in the last slide, but I thought I'd save for it here. Well, actually, I'll just even this. I'll go back to this real quick. So in the last one, QC was 10. FQ was 5. Now, QC is also 2/3 of FC. And that means then that FQ must be the leftover. Well, if it's 2/3 of FC, FQ has to be 1/3 of FC. Which also means then that if this guy's 2/3 and this guy's 1/3, notice this is twice as big as this one should be, because it's 2/3 to 1/3. Well, 10 to 5, it is twice as big. So on a problem like number 2A, when it says RP is 3.5, RP is the shorter one. First of all, LP just physically looks bigger, but LP is the distance from the vertex to the centroid. So if this is 1/3 here, let's just say 1/3, this guy here has to be 2/3, so it has to be double the 3.5. Well, double 3.5 is 7. Now, we know, now it's kind of flipped another one here. I'm going to change marker colors just so I can kind of differentiate. JP is 9. Well, it's the 2/3 part. I'm looking for SP or PS, which is the 1/3 part. Well, again, 2 to 1, but I have the 2, so I need half of it. So I need 1/2 of 9, which is 4.5. Okay. So the longer one's always double the shorter one. And we'll spend time in class talking about that a bit more. Now, the last bit of this section, then, for the video's sake, is one last center, the orthocenter. This is if all the altitudes, whenever all the altitudes are drawn, they'll intersect at a point, and there's not a whole lot to it. So the lines containing the altitudes of a triangle are concurrent, intersecting at a point called the orthocenter. Ortho just means straight, and that's because of perpendicular, so it's the straight center, so to speak, because it's just the perpendicular center. You can see here in the drawing, I've got this set up. Here's the orthocenter right there. Okay. There's no length specialty, there's no circle thing I can do. An orthocenter just exists, so there's not a whole lot of excitement to it, but it does have some weird properties in the sense that it could be inside, it could be on the triangle, or it can be outside, depending upon how it's drawn. But yeah, we do have orthocenters. Okay. Now, for tomorrow, okay, here's your homework. Sorry, this is a little longer than I thought it would be, but there's a lot of little things to kind of cover. So you've got that U is the centroid. Okay, UK is 12. They've already marked that for us. EM is 21. They did not mark that for us, but UD is 9, so they did mark that one for us. So our job is to figure out then CU, MU, CK, JU, EU, and JD. Okay, so good luck. If you have questions, come in, and I'll do the best I can to help you out. Thanks.